Hi, I'm Charles, and welcome to part 10 of the OpenSCAD video series. In this part, we're going to be talking about if, else, and else-if statements, scale, the scale operator, 2D and 3D graphing. So let's get started. So, if statements, else statements, and else-if statements, basically in programming, and OpenSCAD is no exception, they detail certain things that will happen. So under certain circumstances you want something to happen, but maybe under different circumstances you want something else to happen. Or if only in very specific cases you want something done, but the rest of the time you want something else done. So we're going to look at things like that. So we're going to start by declaring a for loop. Just for a good use of example, we'll say I equals a range from 0 to 100, and put our curly braces. And so we're going to say if, this is the syntax for the if statement, if parentheses curly braces. So we'll say if there's some condition, we want to translate a cube. So we want to translate it maybe 2 times I in the x direction. So we have to figure out our criteria, and there's a few things that we can use as our criteria. There's a few different operators that we can use. So there's the greater than symbol. There's the less than symbol. There's greater than or equal to. And there's less than or equal to. Or there's regular equal to. These are a few different operators, and I'm going to show you how to use them. So we'll say if I is equaled to 5. If I is equal to 5, then we want to translate a cube. And otherwise, it'll do nothing. So we should just end up with 1 cube. And that looks like what we're getting. So, I mean, that's not incredibly helpful. We're taking a range of 101 objects, and we just get 1 out of it. So that's not super helpful. So there are methods to get more. So say we want every 5th object out of it. So what we would do, we talked about the modulo operator in terms of objects, but now we're going to talk about it in terms of math. So what it does, the % modulo operator, if you took I and divided it by 5, I modulo 5 would be the remainder. So say you had 6 and you did I modulo 5, then you would get 1 because 6 divided by 5 is 1 with 1 remainder. So if we want every 5th one, we want the remainder to be 0. And that's when the number is divisible by 5. So 5 goes into 5 with 0 remainder, so the remainder is 0. So this will give us every 5th object. So we say if the remainder of I divided by 5 is 0, then we want to create the object. And so now we get every 5th object. Maybe we want every other object. So let's say if we modulo by 2, or divide by 2, the remainder when we divide by 2, we should get every other object. And that looks about right. So now we're going to talk about an Elseif block. Actually, it might be easier to just talk about else first. So maybe we want something else to happen if it's not divisible by 2. So we'll just type else. The syntax is just else. It has to come after an if statement though, or else it doesn't do anything. So we have the else statement and the curly braces. Now the tricky thing, it's a bit of a pain in OpenSCAD, but you have to copy all the code that's in here if you want something similar to happen to what's in your first if block. So we copy it and paste. So now it'll do the exact same thing, but that's not what we want. So let's add, well, not exactly the exact same thing. It'll give us all the cubes that are in between the ones that are defined here. So let me just show you. So it's going to give us all the cubes that are in between, but we don't necessarily want that. Maybe we want something different. So I'm going to define the behavior for what else to do. So let's say, let's add 5 to it. We'll also translate it 5 in the y direction. So now we have a bunch of staggered cubes. So these are the ones where their index, their number is divisible by 2, and these are the ones where it's not. So these are the even cubes and these are the odd cubes, put quite simply. But you know, maybe we have another condition that we didn't cover with our first condition. So we can have more than just one condition. So the way we represent that is an else-if block. So the syntax for that is else if. And we have to have the parentheses because there's a condition, and curly braces. And the else can stay right after it. It's not impeding, it's actually, you can do that. You can have an is, then as many else ifs as you like, and then an else block or no else block, depending on what you want or need. So let's say if in a very specific case, let's say I is equal to 10. If I is equal to 10, maybe we want the cube to not be just a regular cube, but we want it to have a vector to determine its side lengths. So let's say 2 by 3 by 15. So it'll have a very large z value. So we can count, we can figure out which one is the 10th one. Generally, we don't need to do that. But this, for the purposes of this, we can because it's a small number. So this is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this one should change when we change this, and none of the other ones should change. So I'll press F5, and nothing changed. I see what I did. So this is a good learning moment. So since 10 is even, the if statement never got here. So this if statement was evaluated because 10 is divisible by 2. And then it stopped. And then it didn't evaluate any of this. So it just did this and none of this. So I made a little bit of a fool of myself there, but it should work this time. If we do 9 and we count 9, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and we move over here, just this cube should change. And there we go. That did it. We didn't add the y. We can add the y just so it's in space with the other ones. But essentially just this one changed just because it's equal to 9. And you can define special cases like that all day long. Or maybe you could say if it's divisible by 9. So you say if you want every ninth modulo 9 equals 0, you want this to happen. So press F5, and we get a bunch of them that do this. So that's more or less it. Just for if statements and else statements and else if statements. It's the general syntax, how they work. Yeah. Next, we're going to move on to the scale operator. So I'm going to comment this out. So let's say we have a sphere. This is probably the coolest application of the scale. We'll say the diameter is 10, and we'll make it fairly fine. We'll make it 200. So we have a sphere with an FN value of 200, and say we want more of an ellipsoid shape. We want to stretch it in one direction. Then we use the scale operator, which has a syntax similar to translate and rotate. Unlike translate and rotate, you don't want to put in 0, 0, 0 for the scale, because that will shrink the entire thing. It'll scale everything to 0 and you end up with nothing. So nothing happens. In this case, with scale, you want to go 1, 1, 1 as the default value, because that is what will leave it as it is. It scales everything by 1. And so even if one of these values is 0, then it will become flat or 0 or a line or something that's really not usable. So it's probably best to just leave it as 1. You can scale fractions and that will decrease the it'll just squash it. So that can be useful, but probably scaling to 0 is not super useful. So notice that we have 3. We have 1, 2, 3 in our vector, 3 entries, and they correspond again to the X, Y, and Z axes. So the first one, X, will scale along the X axis, the second will scale along the Y axis, and the third one will scale along the Z axis. So let's do the Z axis first. Let's put 2 in for the scaling on the Z axis and see what happens. And we get this kind of egg shape. I guess technically it's not an egg because an egg is a little bit different on the bottom, but it's round, it's like an ellipse. It's fairly interesting. So if you look at it from the top, you can see that it hasn't been scaled in the X or Y directions. It still forms its circle, but if you look at it from any other direction, you can see that it's been scaled in the Z direction. 3 times. You can also, as I said before, you can scale a fraction. So let's do 1 over 3. And you kind of get this flat looking pancake shape, maybe like a discus or something. Another way to achieve something similar is you can scale in the X direction, scale 4 times in the X direction, and we'll scale 2 times in the Y direction. So this looks more like a pebble or a skimming stone. And that's mostly what it does. You can also you can scale things that you've translated or rotated. It's just another transformation. So let's take a rotated cube. Let's rotate it 45 degrees about the x-axis and see what we get. So we get some kind of funky looking shape. So if we get rid of the scale, we'll just see what we start with. Maybe I'll add one more rotation about the y-axis. We get this kind of interesting orientation for the shape. I'm going to take this off, and I think it'll be interesting if we scale in the z direction. So we get this parallelepiped, I guess. That's what you would call it. Yeah, or a kind of diamond shape. Yeah, you can get some interesting shapes out of it. So that's more or less how the scale operator works. Pretty simple. And can be really useful to get some interesting shapes. So that's that. So next, I'm going to be using the method that we talked about in the previous part for graphing, for nested for loops. So we'll just start with basic 2D graphing. So we'll say x is equal to, let's say, -20 through 20. Now, I guess we have to look at what we want to graph. So we're going to start with the x squared function, or the simple quadratic function. And we'll take a look at what that looks like. So we'll go to Google Chrome, and I've already loaded up the Desmos graphing calculator. And the x squared function looks like this. It's called a parabola, and it comes down and goes up, and it has this sort of curve. So the way that we graph that, we're going to use this function. And just something important to note is that essentially what's happening is when you translate a point along the x-axis, there's a corresponding value that you have to translate it along the y-axis, which is x squared. So if you translate it for some x, let's say you translate it 2, then the value you have to translate along the y-axis is 4, because 2 squared is 4. That's essentially it. So that's what we're going to implement. We have something similar for x cubed. Same deal. These are just what the functions look like. It goes down to infinity, or it goes down to -infinity, and then comes up, and then up to +infinity. And these are just what the functions look like. So we're going to graph them. So the first one, we're going to translate cube So the way we start, so now we just have our cube in the middle. That's not super helpful to us. So we first want to translate everything along the x-axis. Now, you don't necessarily have to start with the x-axis, but just for consistency and simplicity, I'm going to start with the x-axis. Also, my variable is named x, so this should keep it fairly simple. So we've translated a bunch of cubes, I think 41, 42. Anyway, a few cubes along the x-axis. And now if we want them to come up like a parabola, then we have to define something for the y-axis or the z-axis, some sort of translation for the y or z-axis. So in addition to something I've said previously, variables can change if they're inside for loops. So we're going to name a variable x squared and we're going to say that x squared is equal to x times x, which is essentially what x squared means. So x times x is x squared, and we're going to put this in for the y value. And see what we get. As you can see, we get something that resembles a parabola. And maybe this isn't the best way to look at it. They kind of disappear after a while, so that's not super helpful. But as you can see, it's kind of following the general shape. You know what I might do? I'll just take this down to 5. And I'll increase the step so that it's clearer. So, yeah, you can see that it follows the general shape of the parabola. And let me just check. It might not be actually going to 5. Yeah, the last value is 4.8. So if we wanted it to go to 5, we just plus 0.2. Yep. And then our parabola is equal on both sides. Comes up to the same point. As we can see in the calculator, it comes down and around just like that, which is what we have here. So, as I was saying, values can change in a for loop. So for each value of x, each value that x takes on, x squared will take on a different value, which is one of the few times that the variables can change. So next we'll do x cubed, which is x to the third power, which is equivalent to x times x times x. There's a simpler way to do this, but for just simplicity's sake, I'm just keeping it with the multiples. We're just multiplying them one by one. For higher powers or fractional powers, there's a POW function. We might cover that later. Anyway, so what we can do is get rid of x squared, and maybe we'll put in x cubed in the z. So as we can see, it generally follows this going down to negative infinity, coming up, and going up to positive infinity, as it should, as the math predicts. So that's good. So something that you can do that's interesting is you can have one function in one direction and another function in another. So we can have x squared in the y direction and x cubed in the z direction. So let's see what that looks like. So if you look from the y direction, it looks exactly the same. It looks like it's not different at all. It goes up, it comes from down and goes up. But then if you rotate your view, it looks more like a parabola. I don't know, I just found this really interesting. Probably this is a good time to explain the difference between perspective and orthographic view or orthogonal view. So perspective view is essentially how you see as a human, where the further away things are, the smaller they get. You can see that the cubes, the further away they are, they decrease in size. Orthogonal is a little bit different like this. No matter how far something is, it's always the same size. So you can see how things line up, if they line up. So all of these are the same size. All these cubes are the same size. And these ones too. So you can get used to orthographic view after a while. Maybe they do shrink, but relative to each other, they should be the same size. So it's good to see if if two things are relatively far away, you can see whether they line up or not. Yeah, that's mostly it. So that's that for that sort of graphing, 2D graphing. You can also graph lines or whatever function you want to graph. Now we're going to do just a little bit of experimentation with 3D graphing. So for this, you need to define two variables. So we're going to define A, the range from -5 through 5, and B is a range from -5 through 5. So let's say 2 times A and 2 times B. And this should be familiar from a previous video. So let's switch back to, well, as you can see that it's a little bit different than perspective view. And you can see that everything lines up. And now if we switch back to perspective, the cubes in the back are smaller than the cubes in the front. So that's probably the main difference. So I did not make the centers true. There we go. So what you can do with this, so in this graph you have two independent variables. You have A and B. They're both independent. And so you have one dependent variable, which is Z, or what's in your Z-axis. So you can define whatever you want. You can say A times B. Maybe I'll move this out. I'll define a variable Z equals A times B. And we get something funky like this, which is kind of like a three-dimensional parabola. Three-dimensional equivalent in a way of a parabola. In a way. I'm going to make it a little bit finer just so it's easier to see. And here's really where it's important to note that the more pieces you add in, the finer it gets, but you add a lot of pieces. So it becomes quite fine, but it might slow down your computer a little bit. So this is the kind of shape that you end up with, which is just pretty interesting, if you ask me. So we'll change this a little bit. We'll say A times B times B. This might be a little bit of a 3D analog of a parabola. Maybe. So yeah, you end up with these interesting shapes. It's fun to play around with. And that's mostly it. You can input any function that you want. So I suppose I should probably show the power function just to make things easy. It's POW, P-O-W. And I think if we do A, 2, this should be A squared. Yes, it is. And then if we multiply by, maybe we should add plus power of B squared. There we go. This is probably the better paraboloid. Yeah, I think this was what I was going for originally. It just looks like a parabola that's been rotated around the Z-axis. Anyway, that's mostly it. I'm pretty sure I've covered most of these things for 3D graphing and if statements and else statements and scaling. At least the basics, I hope. So thank you for watching, and hopefully I'll see you in the next one.